Thank you very much. Thank you very much for giving me the opportunity to speak here. Indeed, the title of my talk is on monomial matrix models superintegrability. First of all, I want to say that this is an ongoing research. So, with several people, and we are going them out as I go. So there are many, in fact, open questions, which probably I also point out. And actually, the emerging structures are not fully clear at the moment. So I will tell you what I know, but what I don't know, I don't know. So structures are not really clear. And then, so I want to start with a little bit of a teaser of the formulas that will be in the end. So, in case you somehow missed the rest of the talk, so the one formula is that the average value in this monomial matrix model, whatever that will be, of a true function is again a true function evaluated at a special point. And so, in fact, these kind of properties are called superintegrability. And then another slightly more complicated formula is that the bilinear value of well, the average of the product of true function with the some special polynomial, the associated polynomial.
So please, here S12, yes? On the
S R.
Where
R,
what does it mean R?
huh?
What does it mean R?
So it's just a Young diagram.
Yeah.
It's Young diagram, and this is the Schur polynomial.
S is a Schur polynomial.
Yes.
Okay. And on the right hand side, S star.
S star means that so the Schur polynomial typically depends on times pk, and so we set this pk equal to some certain values. Well, actually, okay, this maybe I should put in quotes because this is not the full accurate formula. But
it is. It's possible to get this formula exactly.
Yes, but the true formula would be that. Okay, first to make it accurate, maybe write the Gaussian case. So SR of delta K2 times SR of n over SR of delta K1. So there are more than one true functions in the actual formula, and moreover, when in this case of monomial matrix models, this single true function of n is transformed into many.
In the denominator, SR.
Yes, everywhere SR.
Yes, okay.
But of different values.
Yes.
Okay, and so
what's the meaning of your brackets? Can we define that?
No, not yet. But this is just a teaser. So nothing is supposed to be clear at this point. But so another formula that would be hopefully presented close to the end of the talk is that the bilinear average is the product of two true functions. One of them is the skew true function. So evaluate two sets of special points. Yes, and so that's one kind of take away from the document.
Associated means what?
Means that it's made of a function, but there is a formula relating this k delta polynomial with S delta polynomial, an explicit formula. Yes. And so actually the way it is related is with help of the curly O operator, that plays crucial role in the construction of whole WL models. So it's a suitable monomial realization of this WL model operator, which on Thursday, hopefully, Viti Mishnikov will tell you more about. So he will talk a lot, hopefully, about this stuff. I will not talk as much. So now, okay, now the teaser is over, and I continue with the motivation. So motivation to study this subject, and perhaps I should explain why it's interesting to study matrix models in the first place, then why, in particular, monomial matrix models are interesting, and also why is it interesting to study superintegrability of monomial matrix. So at least for me, interest in the study of matrix models is to understand the structure of quantum field theories. But of course, you know that this is a very complicated and ill-defined object. So there are divergences, there are these anomalies, there are all kinds of phenomena. And so one can say that the real world quantum field theory is, so to say, wild and not so easy to understand. So there is a route, a radical simplification one can take. And consider quantum field theory in zero space-time dimensions. And this way, one immediately arrives at the field of matrix models, which are nothing but usual repeated integrals with some complicated structure. And of course, one can point out that there are other ways to go from quantum field theories to matrix models, sort of more advanced ones. For instance, quantum field theory can have a large symmetry group. And so therefore, in some cases, one can use the localization procedure to arrive at certain matrix models. Or it is possible to consider quantum field theories in discrete space-time, and also one arrives at multi-matrix models. And so these integrals are much simpler in a sense they are tame. So in particular, they allow honest non-determinative calculations. And so that is what we are after. And of course, one can do all this honest non-determinative calculations. We discovered that there is a rich set of emergent structures. Which are, well, they are related to both words of the current conference. So there are geometric structures, and there are structures related to integrated systems.
What do you mean by calculation? As with integral?
Yes. So the trick is to get what to calculate. And so examples of this matrix models very much related to, say, geometry are the celebrated Kontsevich model. I hope familiar to the audience related to the integrals over the model aspect of curves. And also many matrix models related to Lewis numbers. many numbers. Yes, so this was the motivation to study matrix model, that somehow they, in disguise, turn out to be related to some mathematical concepts from numerical geometry and geometry of other spaces. So why then monomial matrix models? And so very roughly monomial matrix models are the ones where the Gaussian potential is replaced by monomial potential for trace of x with r. But then it is interesting to study them because they are toy models for perturbation theory around non-Gaussian points. Non-Gaussian. Yes.
So trace is squared is replaced by z. I don't understand what that
Yes,
means.
so for usual Gaussian, for Hermitian Gaussian matrix model, the potential is trace x squared, and for monomial, potential is also simple, trace x over r. And all right, why we are interested in this perturbation theory around non-Gaussian point is, for instance, non-Gaussian. So this is precisely what it means. So the perturbation theory around the potential, which is well, non-parallel. Yeah, so the situation, the physical situation where we might be interested in this is, of course, Young's theory, where very loosely Lagrangian is trace of f mu squared, which is again in very exaggerated way is d mu a mu squared plus g a cubed plus g squared a to the fourth, where g is the coupling constant. And so you can see that in principle, when the coupling constant is large, which turns out to be the case in quantum chromodynamics, actually it is probably more suitable to explain some phenomenon, to expand around this non-Gaussian point rather than around the Gaussian term. But the classical perturbation theory, which is written in quantum theory textbooks, always deals with this, and somehow
Why trace is absolute?
yeah, trace of everything, but I mean, trace is not the only thing that is absent in this formula. It is oversimplified. And so then, well, perhaps to just try to explain such phenomena as confinement, one would be interested in expanding around this a to the fourth instead of a square root. And so here I have the toy model of what happens. So consider just one-dimensional integral. There it goes from minus infinity to plus infinity of dx of e to the minus 1/2 x squared minus lambda x to the fourth. So there are two things one could do with this simple integral. So basically, it is a toy model of this. First is a standard thing. The standard perturbation theory is to assume that lambda is small and expand it into powers of this lambda, and to obtain that it is equal to the following at the moment form of our series. So minus 1 to the p over the factorial lambda to the p, and then the integral of dx of x to the fourth p times e to the minus 1/2 squared. And so this is just the usual Gaussian integral, and it is equal to 4p minus 1 double factorial. And then, so it is straightforward to check that, well, if one calculates the asymptotics of this p-dependent guy, then it is e to the p, and so the radius of convergence is 0, and it is well known that the classical perturbation theory around Gaussian point often is an asymptotic Vauer series. So in this sense, we are not obtaining the two answers. We are obtaining some hint at what the answer is. And to obtain the actual answer, it is possible to act differently in this case, which is to rescale x time, so x goes to x times 1/1/4, and then let us redefine the decoupling constant g equals square root of lambda. And so what will happen is that this 1/g will appear here, but it will disappear here, the lambda dependence. And then we expand in the powers of 1/g to obtain 1/pi sum over p from 0 to infinity minus 1 to the p over p and factorial g to the power minus 2p, and then the integral. So from minus p to plus infinity dx times x to the 2p times e to the minus x to the. And so in this case, in the one-dimensional case, it is well possible to calculate this integral, which turns out to be equal to gamma of pi over 2 plus 1. And now the point is that no, not at all. I mean, so it is an yeah, it's in the standard definition of gamma function. Yes, the scale, so x to the 4th should be some variable t, and you notice also that the integral is symmetric with respect to the origin. So it's actually from 0 to plus infinity or something. So I mean, it is. And so this time when you estimate this p-dependent term, it is equal to, or it behaves as p, at large p, as p to the power minus p over 2. And therefore, the power sum actually converges, and it is possible to actually write down full non-perturbative answer. So some normalization factor times e to the 1 over 32 g squared times a 1/4 1 over 32 g to the 4th. So this is the modified basic function of the second kind. So okay, answer is equal to some special function, which we can check that indeed at g equals 0, this function has essential singularity, which we somehow saw here from this standard perturbative calculation as the radius of convergence turned out to be 0, and also it was the integral itself was divergent for depending on whether lambda it showed was positive or negative.
With k and with 1, it is the same?
No, it is different. It is different. So this is modified Bessel function of 7k. And so the moral was that well, somehow going with this perturbation theory around non-Gaussian point gives us some virtue in particular. So hope is that we will be able to extract full non-perturbative structure of the answer.
So
yes.
G goes to 0, yeah?
Yes.
If lambda goes to 0, there seems to be no problems with this. Yeah.
But there is a problem still with this integral if you expand, because even for small
Yeah,
lambda,
it's a low expression, I see.
yes.
You say that if you set lambda to 0.
Fine. Yes, then how the our series in this lambda is not convergent to the function. All right. So now I need to explain about superintegrability. Okay, so superintegrability is interesting. Well, first of all, the interest in the subject was somehow rekindled in this monomial paper 1705 so 009 76 which somehow so the property itself, at least in the case of Gaussian matrix model that I'll discuss in a moment, was known for a very long time, and also for some other models, but somehow it was never given such a focus of attention. So okay, so we will consider the case of initial Gaussian matrix model and see what happens. And the point why this is important that to any model and any matrix model in particular, there are sort of different layers of stability. So we can solve the model in more complete sense than another. So let me describe it later. So first is that the model is unsolved, or in other words, the definition of the model. And the definition of the Hermitian Gaussian matrix model in this case is that I'm evaluating averages of any function of traces of a matrix X, and so this is nothing but integral of the space of Hermitian matrices, like matter and with potential integral minus 1/2 traces squared, where I put this f of X under the integral, and the typical functions that one studies are the so-called correlators, which are nothing but the averages of product of some traces. So variables like that. And then the
Why it is indicated as solved?
unsolved.
Unsolved. Why?
Yeah, because we haven't solved it yet, we just defined it. And so the point is that if there is nothing more than this integral that we have, the only thing that we can do basically is to calculate particular f of x for particular values of, say, k, and for particular values of n, which is the size of this matrix. And just obtain some numbers with no structure. But so it is possible in the case of matrix models often to go further. And so I don't know how to properly formulate it, but let me say that matrix models, matrix integrals can often be solved by procedure. What I mean by that? Well, in the language of typical matrix model, one can define the infinite set of so-called word identities, and in a sense replace the so this integral then becomes a particular integral representation of the solution of this infinite set of order identities. And the way to obtain such order identities is to write under this integral full derivative, full matrix derivatives of certain function, and then of course say that this integral of full derivative is 0.
What do you mean derivative by matrix?
So in the language of say, so nothing depends on the angular variables here of the matrix X. So let's say we transform this integral to the integral over eigenvalues of this matrix. And so then what we actually insert here is sum or I from 1 to n of d over dxi times xi to the sum power n plus 1. And so this is the operator you insert, and here you write e to the minus 1 half sum x y squared, and here you write this correlator. So then you notice that on one hand side this integral is clearly 0 because it is an integral of full derivative.
But it is not by definition.
It is an I would say immersion property. It is an observation. So on one hand, this is 0 because by virtue of Newton-Davis formula, it is equal to the values at the boundary, and thanks to this exponent vanishing at the boundary and damping all these monomial factors, it is 0. On the other hand, I can act with this derivative on every term here, and so the result will be sum of particular correlators. So the result is that for any correlator, I can write that so C n plus 1, and here a multi-index is equal to C n minus 1 I plus some extra terms, which I do not want to write in detail. And so what I mean then that the matrix model is solved by procedure. That if I'm now interested in any particular correlator, particular values of vector k, I can now plug it into this recursion, and iteratively calculate it, and then obtain an answer which is already symbolic in the matrix size n. So
why here it is many unities or not? What do you mean by why here?
By why? I mean that the multi-index I want
Yes, many unities.
Not unities, but any
Okay,
numbers.
okay. It's
Any numbers, and then I select the largest.
multi-index. Okay.
Yeah, multi-index. And also, okay, I need to supplement this with the initial condition. So C with multi-index and then 0 is equal to n times Ci, and C of empty set is 1. So I start with the initial conditions, then I use this recursion procedure and obtain any correlator as symbolic function at n. So this is, and actually the logical recursion procedure, which is somehow the mathematical avatar of these model identities, at least in some cases. But it is also a kind of solution by procedure of, at least from the point of view of matrix models, it can be viewed as solution by procedure of the matrix models, in the sense that given initial data, so the function x, y, and the Bergman kernel, one then, using the standard logical recursion procedure, which I very similarly write like this, can calculate any omega gn to any desired order. But one does not know omega gn or any gn in advance. That's the point. And then, so the third level, which is exactly this superintegrability, which is possible only sometimes. So we do discover more cases when it is possible, but and one can argue that it is only possible in very simple special cases, but then the model is sort of combinatorial. So. And this is exactly how I announced in the teaser. So consider a special basis of functions, which is set once for all. So in the case of Hermitian Gauss-Matrix, these are two functions. And so typical examples are S2, which so the function depends on the integer partition, and it is completely combinatorial object related to representation theory of symmetric groups and linear linear. So S2 is equal to pi1 squared over 2 plus p2 over 2, and say S11 equal to pi1 squared over 2 minus p2 over 2. So what will happen if I plug here instead of pk raise of x to the k, and then evaluate this integral. For instance, with help of this recursion, then I will discover, surprisingly, that the average value of this S2 of x is equal to 1/4 n times n plus 1, and the average value of S11 of x is equal to minus 1/4 of n times n minus 1. And so one can see this simple formula, the remnants of the construction, because so you see, if I plug here every t equals n, then here I will get this n times n plus 1. And here I will get this n times n minus 1. Moreover, if I plug here pk equals 1/2, so this special pathway, then what then? Okay, yes, one. Then delta k2. Then, okay, this vanishes, and then I get 1/4 and minus 1/4. So, in this sense, so the description turns out to be true, and the general formula is that here, as this 1/4 is SR of delta K2, this n over n minus 1 is the ratio of two functions. So one is just of all the k equal n, and another one is of delta. So only the first time is non-zero and the zeros, which is just the combinatorial factor, which is not seen here, but it is related to the product of lengths. This is also, so if you study more examples, then you see that it is there. Yes, and so you see now that the model, the distribution Gaussian matrix model, is solved in a much more complete sense than previously. So previously we had to laboriously go through this either order identities procedure or topological recursion procedure. But now what we do, if we want to know some correlator, we just expand, so to say, correlator like this. We just expand it into the basis of true functions, which is maybe a tedious problem, but it is a problem of a different science. So of combinatorics. And then for every individual true polynomial, we immediately know the answer. So that motivates why we do want to study the superintegrability, and we actually want to have as many superintegrable models of which we know that there is superintegrability as possible.
Generic correlators, which are on top, are more, if you compute them, you can complete the yes. You say that the answers are more complicated functions than the answers to true polynomials.
Yes, for true polynomials, they are instance trivial.
Yeah, some polynomials in n, yeah?
Yes.
So those are not some polynomials. What else can be?
Yeah, but the point is that here we know coefficients of those polynomials in advance. So they're not just some polynomials, but very completely the true functions.
Did you say that this fact functions was noticed by neuronal process?
No, not really. So this character expansion, so it already appears in the review of Maroda from 90 something. So it was then discovered in some papers of the report, something like that. I unfortunately don't know the precise reference. But, yeah. It was just put in the context in the paper. Okay, so how much time do I have?
So, no, more or less, so,
Until it's okay, yeah. All right. So then I hopefully explained why the subject is important. And this is all old stuff. So superintegrability of permission Gaussian model and this one-dimensional integral, this is all well known quantity. So then let us finally arrive at monomial matrix models. And so now I somehow sketch some of the results of our old paper with Cordova, Heidenreich, and Ramishna Kirov myself. So 1611 times 0.03 1. So where we first considered these monomial matrix models. And of course, so the definition then, the average value of x is in the language of integral over eigenvalues. So as I said before, the only thing that happens is that we substitute the potential term with x to the power r, raise x to the power r, which in the language of eigenvalues looks like this. And then there are of course
Vanderbilt.
yeah. This is fundamental determinant. There are a couple of technical, but in some sense conceptual issues that arise in this fundamental case. And first of them is quantum dependence. So let us consider case R equals 3, which is the first non-trivial case. So one can notice that the e to the power minus 1/3 x cubed, the one-dimensional integral, only converges if so first of all, it doesn't converge on the real line, right? When integrate this over the real line. So what one should do instead, and this is, if you will, some slight redefinition of the problem, is to consider the contours that go from one convergent Stokes sector of this e to the minus x cubed to the other. Or, well, in that paper we found that it is much more convenient to consider the following contours. So first of all, some contours vi, which go from 0, the rays vi, which are like that. They go from 0 to some direction defined by the i's power of the primitive root of unity. And then from these basic contours, one actually assembles contours CRA. which are in a sense they are Fourier transform of those BI. So one sums with these BIs with the following imaginary coefficients, and so one can check that at zero there is actually no boundary of this contour. So the boundary of this maybe complicated contour is still somewhere in here. And so this is the good contour to integrate our eigenvalues over. And with this definition, it turns out that the integral, the one-dimensional integral, first of all, just one eigenvalue of x to the p is equal to gamma of p plus 1 over r times this new symbol which I want to introduce, which is the selection rule. So when p plus 1 minus a, where a is the number of the quantum, is divisible by r, then the integral is non-zero, and it is zero otherwise. And so actually the point is that in principle, we have these n eigenvalues, and each of these eigenvalues can have its own integration point. But no one knows anything non-perturbatively about the answers in this sector. And so in this paper was decided the case of so-called pure phase, where so we choose one set.
When you say non-perturbatively, in which variable?
No, I mean that for this non-Gaussian matrix models, one can consider the diagram path of phase, where so one assumes that there are some eigenvalues sitting in each minimum of the potential, and somehow, but also then so this is transformed to generic power R potential. And there are some techniques and structures related to the situation where when in this potential some eigenvalues are seated in different minima or extrema, I should say, of this potential. But it is important that every extremum is quadratic. Yeah, but and here this fact that different and I are sitting in different potential extrema is related to the somehow to the choice of different contours here. Somehow.
Yeah. So you can find, for example, for this answer that goes out of this integral. But if the function is the case of which number of eigenvalues. Right?
Yes, yes. So
when you fix basically when you say that some fraction positive is minimum or maximum or extrema,
yeah.
exactly corresponds to certain choice of contours.
Yes, yes. And so in this sense,
Then you can find, yeah, but what do you mean by non-perturbative?
Non-perturbative means that in this case we can find an answer. Find just the non-linear, if you will. But in this very simple case. Okay. And also it is in this paper we consider the case it turns out so this case of even monomial matrix models is tricky. In particular, so the partition function, which is just the average of unity, is non-zero only when so it somehow depends on the size of the matrix. If we decompose it with respect to division by R, and so B is the remainder, then partition function is non-zero only when B is either 0 or equal to the number of points. And so this was the case that we considered in this paper, and we found out, first of all, that this Z itself is a full factorized expression, so is a product of gamma functions, which I don't want to write, but close to the point of today's talk, the normalized average of true function is a generalization of the Gaussian formula. So now, instead of this SR of delta K2, I have S lambda of delta KR over R. Where here I probably, yes, not the two. And then times the peculiar psi factor, or rather should I say the monomial generalization of this psi factor, where this psi factor is equal to the product over the boxes of the Young diagram of still n minus I plus j. So same as there, except that now here the funny double square brackets appear, and what they mean is that, so if I draw a Young diagram, then this is just the product over those boxes or those diagonals on the Young diagram, which either have their, so suppose I consider I minus j, the number of the diagonal, and so the remainder of the modular R is either 0 or A. And so that
you say that for some reason there is an answer, but how do you do that?
how do you prove them? That is a very interesting point. So, so yes. So in this case, there actually are proofs, in contrast to what I will talk about later. So how you do? You define. I will now say only in a very sketchy way, but you define the vector orthogonal polynomials. In the sense that so usually you define orthogonal polynomials in such a way that their pair integral is proportional to L to the Kronecker delta. But in this case, there is a proper monomial generalization in the sense that the relevant matrix is the block matrix, where there are these interleaving of A times A block and R minus A times I minus A block, where each block is off diagonal. So this is the slight generalization of orthogonal polynomials you have to consider, and then you notice that both the partition function itself and actually also the average of the Schur function are determinants. So they are expressed as determinants. And this change to the basis of orthogonal polynomials from the basis of xk is a triangular change of variables which transforms the matrix of which you consider the determinant to, say, upper triangle. So then you know how you quickly obtain the answers. Yes. So this is all the normal stuff. And then what is first quickly unknown stuff. Depends on the count.
This correlator you just clean, yeah, you just clean now.
Yeah.
Because it is first well, you don't have it right?
Yes. Yeah.
And use that in
And
it can be easily computed or what is the relative computation. Because there you have some authority which I don't know what it is. And those function keys just have polynomials, which are no variable. Yeah.
Yes,
And so those correlators were expressed in terms of Hermite polynomials.
but
But are they known or not? I didn't get from you.
but even though they are in principle calculable using polynomials, you still don't know the precise formula, so you have to go through the calculation.
I think for the Gaussian case, the correlator can be expressed by not polynomials, but polynomial functions. So it's an analytic function on the complex plane for the size of the matrix.
Really?
Yeah, because there is a symbolic formula for polynomial functions, and in that case, in that symbolic formula, the coefficient will give the correlators for Gaussian case.
Yeah, well, I just read that the answer is really something different. Made of this
Yeah.
times.
But it's determined.
For the finite size partition function,
Yeah.
if you want correlators, you need to do a symbolic expansion.
So those correlators, they are in for finite size.
Yes, I mean, for finite size, for polynomials, there is, it is a function of n, and also lambda or x, which is the spectral parameter. And when I say the symbolics is that lambda goes to infinity.
Here you kind of integrate. In the form.
Yes, so in fact, what is important is not the shape of the polynomial itself, but rather the average value of the scalar product between two orthogonal polynomials, which turned out to be expressible in both in case of this pure-phase monomial matrix models and in case of Gaussian matrix models through particular gamma functions, which are simpler than Hermite polynomials. But then I wanted to talk about two more topics. So one is the exotic pure phase of the monomial matrix models. So and this is the joint work with the Silver Lucian. So 2204, 14,074. So the question is, okay, so that is non-zero for such particular values of b, but can we say something about other values of b? And the surprising answer is that indeed, so first of all, the observation is that some values of integrals of two functions belong to normalized averages for arbitrary mean. Are nevertheless non-zero. And it turns out that first of all, there is a certain sort of basis partition rho, which very surprisingly is a rectangular partition with sides b times r minus either b times a minus b or b minus a times r minus b, depending on whether a is less than b or a is b to the power, right? Because so this is from 0 to r minus 1. The remainder is also from 0 to r minus 1, so they can interplay. So this is particular law. And then the integrals of the functions are precisely those are non-vanishing, which of those partitions where mu has rho as its R4. So this is the topic which I haven't explained at all, but very briefly, it is contained in the famous Magnolia book. So partitions can be divided by integer number, and so from this you obtain several ingredients. So one is this R core, and another R is the set of R quotients. lambda 0, lambda r minus 1. So this is just an combinatorial procedure which is somehow related also to the isomorphism between the basis of EP, so Maya diagrams, and the basis in RTP. So this are copies of Maya diagram. And in any case, this is the manifest combinatorial construction, and somehow this R4 starts to play a role in the construction of this monomial matrix. And so the normalized function turns out to be equal to, so I promised you a skew function, and here is the first time where it appeared. So now the only generalization actually of this formula is that now here we have skew function. And then the relevant psi factor, so the product over diagonals of M diagram is now such that the diagonals are basically shifted by this minor M, and there is nothing more that happens. And so, even though we in the paper we didn't provide a proof, but I expect that it should be completely similar to this one, because still we are in the realm of usual non-beta deformed matrix model, and so still Schur polynomials are determinants, and still we can define this vector orthogonal polynomial, so I do not expect any complications. Yeah, we checked this work with like numerous large partitions, so I'm reasonably sure that this is the case. And so, final thing I wanted to tell you about, which is actually ongoing work together with Popolitov and Vitiushnikov. And Shanfeng Zhang. Is related to these bilinears that I have integrability correlated, where we consider still the case of pure phase, and where the simplicity the partition function is non-zero, so B is either 0 or A. But now we consider linear relators of Schur function times some other polynomial, and the point is why this is non-trivial is that so from this monomial matrix model already in this paper there is this logarithmic generalization. And there is a formula for a pair Schur relator in this log model, but where the place of x of one of the arguments of Schur function is shifted by some number, and the point is that limit to usual monomial matrix model corresponds to taking v goes to infinity, and in this limit this formula does not work because this infinite v completely shadows this x somehow. This superficially, so well, there is no limit from this known formula, and it turns out that still there is a bilinear formula, bilinears with an integrable formula in monomial matrix model in pure phase, which looks like this. That still I get the psi factor, and then still I get Q should polynomial of delta K R over R, but here I have not this delta partition, but instead a peculiar permutation of this partition. So remember I told you that when you divide partition by a number, you get these arc motions. So what happens is that in this pi delta, this arc motions of delta are reshuffled in a particular way. So delta I goes to delta minus I plus R minus 1 plus A minus 2 mod R. So this is the reflection of modular R. It does look very puzzling when you first encounter it. And so now mathematically this formula is a conjecture. Moreover, in the case, so it is so only in the case when both delta and R have trivial arc words. Otherwise, situation is more complicated. And even so, when at least one arc word is non-trivial, already this superintegrability structure is destroyed in the sense that the result does not factorize in n. So one of the interesting properties of the superintegrability formulas is that this pi factor is a product of simple n minus I plus j factors, which are linear in n. And so for non-trivial arc course, this is destroyed, but for trivial arc course, okay, we have such a formula, which at the moment we have no idea how to prove, but we are working on it. Yeah, so I think I answered. Okay, thank you very much. Questions or remarks?
But I put with question, what do you mean unsolvable by definition?
No, it is when we start the definition, we haven't solved it yet. So it's not unsolvable definition. It is yet unsolved. When we only what we have is the definition.
In the Gaussian case, there's no the changing series of these correlators in the solution of the latest hierarchy.
Yes.
Do you expect anything similar or arbitrary?
I think that it should be a solution to RTP. But this is just a wild guess, but I think that since these arc motions and arc cores are playing such an important role in the combinatorics of the whole story, that probably is some problem.
When you consider just trivial arc cores, is it somehow connected to some kind of reduction of TP equation, like equal to Jones connected to TDV?
I'm not sure, to be honest. And so regarding this relation with integral hierarchies, we haven't thought much.
I have a comment. I think for arbitrary R, but of course there are still maybe some difficulty, but I think for any R, the corresponding is also satisfied two dialectics. And the point is that
just expression on a different point, right?
yes, yes.
So we actually have for the potential, right? No, okay, yes.
So the point is that in this case, so for example, when R equals 1/2, it will correspond to Laguerre matrix model. So for general R, it's similar, but what we call it kind of phase transition compared with GUE. So if this measure is not the information of Gaussian, then it can be obtained from GUE by shifting constant. But in this case, it is not related to GUE by shifting the constant. So it's a phase transition, but satisfy the same into the system. So I also use for this manifold to give a complete answer.
No, maybe. So, in the sense that, so for sure, if one treats potential v of x in this digraph alpha way, then yes, it is a function of Toda, but I don't know. So what I don't know is that when you go to this fully monomial case, whether some new relations with mathematical systems will appear.
Can we understand